Here's one of my favorite problems. But unfortunately, the first time I saw this problem, I stumbled across the answer before I had time to think the problem through. So I'll never know whether I would have been able to figure it out. But on first look, with the three dots, that implies a pattern where we have binomials where it's a variable a take away a variable x, multiplied by another one, b take away x, multiplied by c take away x, and so on through the alphabet, which implies there's 26 binomials being multiplied here. So my first thought was that, well, one of the terms is a times b times c times d, etc., all the way to z. And there's got to be another term, which is x to the 26th power, and numerous other terms, too many to even comprehend, because in previous lessons we've typically just multiplied two binomials together, and in one example we cubed a binomial, which was the equivalent of multiplying three binomials together, but certainly never 26. Well, if you want a minute to think about this problem, turn off the video. But now I'm going to give you a hint. Let's take a look at the way this pattern goes. It would bring us to the back end of the alphabet. And if we look at the back end of the alphabet, we see that the last three binomials are x take away x, y take away x, followed by z take away x. Perhaps you've figured out how this simplifies by now. But if not, here's a reminder. Any number take away itself, of course, is 0. So one of our 26 factors is 0. And then, of course, we all know that any number times 0 is 0. So this expression simplifies to 0. And the reason I bring it up is because in the previous section, we did a lot of factoring. Well, here's a trinomial, but it's not just a trinomial written as an expression. It's a trinomial equal to 0, so we have an equation. And since it has degree 2, it's a quadratic equation. But we can factor the polynomial on the left side, so there it is. And then, since anything times 0 is 0, one of those two factors must be 0. So either the x plus 4 is the 0, or the x plus 5 is 0. Well, if the x plus 4 is 0, then x has to be negative 4. And if the x plus 5 is 0, then x has to be negative 5. And those are the two solutions to this equation. And if you want to check them, substitute the negative 4 in for x in the top line. Also substitute the negative 5 in for x in the top line. And you'll find that both of those numbers work so that x squared plus 9x plus 20 is equal to 0. Well, that brings us to a new property, the zero product property. If two or more numbers have a product of 0, then at least one of the numbers must be 0. Or, for any numbers a and b, if a times b is equal to 0, then either a is 0 or b is 0. One textbook I worked with referred to this as the converse of the multiplication property of 0, but I like the sound of zero product property better, and several textbooks use this as the name for this property. Well, here's a binomial. We can still factor it. The greatest common factor is 3x. Now we've written it as a product of two factors, so either the 3x is 0 or the x plus 5 is 0. Well, if 3x is 0, then x has to be 0. And if x plus 5 is 0, then x has to be negative 5. So 0 and negative 5 are the two solutions for this equation. Well, here's a difference of squares. So we factor it. And either the x minus 4 has to be 0 or the x plus 4 has to be 0. So, of course, our two solutions are 4 and negative 4. Here's one. It's not a quadratic equation, but the zero product property can be used in any equation that can be factored. So we factor out the common factor, which is x, and then we factor the trinomial, which was the other factor, and now we have three factors. Either the x is 0, the x minus 8 is 0, or the x plus 2 is 0. So our solutions, of course, are 0, 8, or negative 2. So this equation had three solutions. Here's an equation with the greatest common factor on the left side's trinomial. So we factor that out and we get 7. And then we factor the remaining factor, which is a trinomial. But of course, while 7 is a third factor, it can never be 0. So we can just kind of toss that aside. The factor that could be 0 is x plus 1. And also x minus 4 could be 0, which gives us the two solutions of -1 or 4. Two solutions for the equation shown at the top. And here's one which is a perfect trinomial square. So the two factors are identical, and we can split them and write them as two separate equations, but we're going to get the same answer for both. So this equation just has one answer. The solution is 7. Here's the difference of squares, but there's a greatest common factor, so we'll factor that out. And we still have a difference of squares, but they're smaller numbers to take the square roots of. And we get this. And of course, 4 can never be 0. So the two factors that could be 0 are 2x take away 3 or 2x plus 3. It takes an extra step. We add 3 to both sides on the left equation. Then we divide by 2 to get one of our solutions is 1.5. And on the right equation, we add -3 to both sides. Then we divide by 2, and we get -1.5. Here's an equation which is definitely not a quadratic equation, but if we're able to factor it completely, we'll be able to find all of the solutions. Currently, it has two factors, a binomial times a trinomial, but it's possible that each one of those can be factored further. In the binomial, we see a greatest common factor of 2x, and in the trinomial, we can break it down as a product of two binomials, x plus 9 and x plus 6. Now, of the four factors that remain, we notice that the 9x squared minus 25 is a difference of squares, and it can be factored even again. So we factor that remaining factor that isn't already prime, and now we have 1, 2, 3, 4, 5 prime factors that multiply to make 0. So we're going to break it into 5 small equations to get our 5 solutions. The first one is 2x is equal to 0, or 3x take away 5 could be 0. 3x plus 5 could be 0. X plus 9 could be 0, or x plus 6 could be 0. And of course, if 2x is equal to 0, we divide both sides by 2, and one of our solutions is 0. The next one is a two-stepper. We add 5 to both sides and then divide by 3. So one of the solutions is 5/3, which could also be thought of as 1 2/3. On 3x plus 5, we add -5 to both sides, then divide by 3, and we get -5/3 as another solution. On x plus 9, we add -9 to both sides, and one of the solutions is -9. And on the final equation, if we add -6 to both sides, our fifth solution is x equals -6. So to finish this off, we'll write our answers from smallest to greatest: -9, -6, -5/3, 0, and 5/3. All 5 of those numbers are solutions to the equation at the top. And here's one where one of the sides isn't equal to 0. So we'll perform some transformations to make one of the sides equal to 0. We're going to add -50 to both sides. We're also going to add 10x to both sides, which will give us x squared, take away 5x, take away 50 is equal to 0. Then we factor that trinomial to give us these two factors, and if either one of these factors is equal to 0, we'll have a solution to the problem. So our first solution is 10, and our second solution is -5. Here's another one where neither side is equal to 0, and it looks like we're going to have to deal with a cubic equation, but then we recognize there's a 4x cubed on each side, so we take away 4x cubed from each side, and we're left with a quadratic equation, and we're going to add 12x to both sides, and this is what we have, and this is not the hardest problem that we've ever done. There's our two factors, and either x plus 10 is 0 or x plus 2 is 0, so the two solutions are -10 or -2. Some equations can be solved using factoring. First, perform some transformations so that one side of the equation is equal to 0. Then factor the other side of the equation, and use the zero product property to find all of the solutions to the equation.